your enthalpy, and types of enthalpy. And we had to start from spontaneity. Okay, we will today mainly focus on spontaneity, entropy, and we will cover everything till the thermochemistry portion. So let's start. All right. So the first law of thermodynamics, it tells us about the relationship between the heat absorbed and the work performed by a system. Remember, what was the first law? The first law was delta U is equal, delta U is equal to Q plus W. Q is the heat exchange and W is the work performed. Delta U is the change in internal energy. This we had already covered. Then the first law of thermodynamics is over. We have already established a relationship between the between heat, work, and delta U, which is the internal energy. Now, how will we determine that a physical and chemical process will happen on its own? Which means, how will we determine if it will happen spontaneously or not? Okay, this is our next target. All right, all naturally occurring process, if they are spontaneous, okay, whether chemical or physical, will tend to proceed spontaneously in one direction only. Okay, for example, a gas expanding to fill the available volume, burning in a dioxygen to give carbon dioxide. All these are examples of spontaneous processes, and these are usually irreversible. Why are they irreversible? Because the reverse process is not so spontaneous. Okay. For example, heat will not flow from a colder body to a warmer body on its own. This is important. Spontaneously, the heat will not flow from a colder to a hotter body or a warmer body. Similarly, a gas in container will not spontaneously contract into one corner. Or similarly, carbon dioxide will not form carbon and dioxygen spontaneously. All these reverse processes will not be occurring on their own. So, what is the driving force of that is spontaneously driving these reactions in one direction? What determines the direction of a spontaneous change? So, we'll try to establish some criteria. Okay. So, first we'll try to define what a spontaneous process is. It is an irreversible process, okay, and it may only be reversed by some external agency. On its own, it will not be reversed. Okay. So first thing which we need to establish for a spontaneous reaction is the change in enthalpy in the reaction. So tell me, by using some sense, if some amount of reactants are getting converted into products and this is a spontaneous process. This is a spontaneous process. So tell me, will heat or energy be released or absorbed in the process? What should be the answer? Will the product give some heat or will the product absorb some heat? It is happening spontaneously. No work or no external help is being given. Definitely the answer will be, yeah, the heat it should be released. If at all it is being released, it cannot be absorbed, because to absorb a heat, you have to add some energy into the reactant. Then only the heat will be absorbed. That means it is not spontaneous. But if heat is getting released, which means, yeah, it can happen on its own. It can release the heat on its own. No need for us to interfere. No need for any other external driving force to be interfered. And we all know, if energy or heat is being released, then the enthalpy change in the reaction will be negative. This is one criteria for a spontaneous reaction, which is called spontaneity criteria. Right. Okay. So they have given one example. Similarly, this is formation of ammonia, formation of hydrogen chloride, and formation of water. Similarly, they have given example of formation of nitrogen dioxide, formation of carbon disulfide. Okay. So the first set of reactions are clearly exothermic. So the decrease in enthalpy in passing from reactants to products may be shown for an exothermic reaction on an enthalpy diagram. They have given an enthalpy diagram to show that there has been a net evolved heat, because reactants are more, they have more enthalpy, products have less enthalpy. So there has been a release of heat. So exothermic reaction, as I told you earlier, if there is a release of heat, that will be a spontaneous process. Now let's look at some exceptions. First exception is formation of nitrogen dioxide. It is an endothermic reaction. Second is formation of carbon disulfide, which is again an endothermic reaction. Okay, these reactions, although endothermic, are also spontaneous. Why and how? We just saw that only exothermic reactions can be spontaneous. That does not, it is one of the criteria. It is not the only criteria. Okay, only criteria is not of enthalpy. There are other things. Okay, in the enthalpy diagram, we can see that reactants are less in enthalpy and products are more. So some heat has been absorbed from the surroundings. It becomes obvious that decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. Then what is the second point? Second point is something called your entropy. Okay, let us examine a case in which delta H is equal to 0. There is no change in enthalpy, but the process is still spontaneous, which is there is a container with a separation in between, and in both the parts of the container we have filled different gases. Let us say the white gas and the black gas. So as you can see in the right partition, there has been a filling of the white gas, and in the left side of the partition, black gas is filled in the container. Now what will happen if I just remove the partition? Okay, if I just remove the partition, let us examine the process. Before the partition, if we were to pick up the gas molecules from the left container, we would have got what? The black gas or the gas A. Similarly, in the right, we would have got only gas B or the white gas. But now after removing the partition, they will get mixed. Both of them will get mixed. They will mix with each other. Now if I try to take a sample from this container, be it from the right side or the left side, we cannot say that we have only gas A or gas B. The system has become less predictable or more chaotic, right? The system has become less predictable now. We cannot accurately predict which kind of gas we will get if we take a sample. So there has been some degree of randomness introduced into the container. Random. There is a random possibility that you might just find a white or just black gas. So randomness has increased. Here we try to introduce one more term, okay, which is called the entropy, and it is denoted by S. Okay. So the above mentioned disorder is a manifestation of entropy. What is entropy? Entropy, if I try to give a small definition, it will be a degree of randomness of a system. Degree of randomness of a system. If we define a system, we have to define an entropy for it. And entropy is not constant for the system. It might change. Suppose we have, okay, I'll give you, it will take 2 minutes. I'll give you one small example of how you can increase the entropy of a system. I'm taking a system, and through a series of changes, I'll try to increase the randomness in the system. I'll make the system less predictable. Okay, this time there has been no partition thing. I'll take a different kind of example. So let us think that some molecules, red beads are present, or a red molecule is present in the container. I divide these red unequally. Okay, now a red molecule I have divided unequally into a small green part and a large yellow part. Okay, here a small green part and a large yellow part. So I will have 4 large yellow parts, that is just for maintaining the equilibrium, and I have similarly small green parts. Now imagine hundreds of changes like this. Here we have just done with 4 molecules, but imagine this system is filled with thousands or millions of such red particles, and with some chemical or physical process, I break these particles into yellow and green particles. Right now, if I take a sample, it might have only green, it might have only yellow, or it might have both green and yellow. So what do you think? Has the system become more random? Yes, the system has become more random. So this is, we'll say that the system has become more random and entropy of the system has increased from the initial value. This is what entropy is. The more random, the more, chaotic you make a system, the more its entropy will be. And if reactants are giving some products, which we can see in this case, with subsequent release in entropy, or entropy is increasing in the process, that process is automatically spontaneous. If entropy is increasing in a process, that process is automatically spontaneous. Okay, right. Let us examine some points about entropy. The greater the disorder of the system, the greater is the entropy. Okay, they have tried to quantify the entropy also. One way is to calculate the degree of disorder or chaotic distribution of energy among the molecules. That would be through statistical method, but we cannot do it here. Just let's just put entropy in a random relationship with heat. Whenever heat is added to system, it increases molecular motion, causing randomness in the system. Thus, heat has a randomizing influence on the system. Then can we equate delta S with Q? So we need to create a relationship between these two, a random relationship. And that relationship is summarized as this. This formula is important. How to relate entropy of a system with heat transfer. So entropy is, change in entropy is the heat which has been passed or which has been taken out. It should be reversible divided by the temperature of the system. Okay, right. Let's explain why is delta S inversely proportional to temperature. First point, delta S is directly proportional to heat. The more the heat you add, the more spontaneity, the more delta S will be positive, or the more the entropy will increase. Randomness will increase more. Just a second. Session right. So this relationship is easily understood why it is directly proportional to heat. But why is it inversely proportional to temperature? The answer to this question is, suppose you add, this is T1 and it is very low. Suppose you add some heat into a very low temperature system. And suppose you add T2, it is high. Let's assign values also. T1 is what, 100 Kelvin, very low temperature. T2 is some 10 to the power 5 Kelvin, which is really high. Now you add equal amount of heat to both. Where do you think the entropy will increase more? Yes, the entropy will increase more in the low temperature system. It will be more, it will become more random. Yeah, anyways, the entropy will increase more in the low temperature system. That is why it is inversely proportional to temperature. Right? The total entropy change for the system and surroundings for a spontaneous process, it is given by delta S total is delta S system plus delta S surrounding. When a system is in equilibrium, the entropy is maximum. So in equilibrium, entropy is maximum and the change in entropy is zero, because in equilibrium, everything is, the properties become more or less static. Okay. We can say that entropy for a spontaneous process increases till it reaches maximum until it reaches equilibrium, right? Entropy is also a state property, so we can calculate entropy in a reversible process by, here. Delta S of system is heat divided by temperature. We find that both for reversible and irreversible expansion for an ideal gas, under isothermal condition, delta U is zero, but delta S total is not zero for irreversible process. Thus, delta U does not discriminate between reversible and irreversible, whereas delta S does. Because definitely, we can find out the answer in this equation. Definitely, delta S system will be zero, but delta S surroundings may not be zero for an isothermal reaction. And you can see the delta S system also, it depends on the heat and temperature. It does not depend on work. It does not depend. So it does not depend on change in temperature. And if temperature is constant, we can also say that delta S system might also be not zero. That is why we say that in isothermal process, it is really easy to quantify the entropy because delta U is zero. Okay. Let's move to another term called Gibbs energy. Right now we have been through internal energy, which is delta U, enthalpy, which is delta H. Now we will see another kind of energy, which is the Gibbs free energy, or we denote it by G. Let's see what it means. For a system, the total entropy change decides the spontaneity of the process. But most of the chemical reactions fall into the category of, again, closed or open systems. Therefore, changes in both enthalpy and entropy, it is clear from the discussion that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change. So there has to be some relation between the two factors which we have discussed, which are enthalpy and entropy. Right? We have discussed these two parameters which are helpful in determining the spontaneity, and there must be some relation between these two. This relation is established by Gibbs function, Gibbs energy, and the relationship is this: G is equal to H minus T delta S. This is the relation. Now, if you just put a delta here, you can put a delta. Delta G is equal to delta H minus T delta S. Right. What is Gibbs energy? Gibbs free energy. Okay, so Gibbs free energy is basically the free energy. Delta U is internal energy. It is like kind of all the energy that is present in the molecule, right? But all of it might not be useful to us or useful to chemists, or it might not be able to do work, meaningful pressure volume work. All the energy which is present in the system might not be useful, might not be able to do work. That is why we have to determine a different kind of energy called free energy, which is free to do the work which we have to, which this free energy only can tell us if a process is spontaneous or not. If the change in free energy, here, let us look at this section. Delta G gives a criteria for spontaneity at constant pressure and temperature. How? If delta G is negative, the process is spontaneous. Why? Because delta G negative in a reaction symbolizes that the reactants have more free energy than the products. Products have less free energy. Definitely, the reactants having more energy will like to go to the products, will like to transform themselves into the products, which are having less free energy. Similarly, if delta G is positive, the process is non-spontaneous. Right. Note, if the reaction has positive enthalpy change and positive entropy change, it can be spontaneous when T delta S is large enough to outweigh delta H. Right. So, using the Gibbs energy, we can now explain the observation which we had made where delta H was positive, but still it was spontaneous. How? How is it spontaneous? It is spontaneous because delta G here is negative. No matter what, there is no exception for delta G. If delta G is positive, it has to be non-spontaneous. Why? Because free energy change is not feasible in that delta G positive reaction. Okay, let's come back here. Delta G is negative. How does delta G become negative when delta H is positive? We know the equation delta G is equal to delta H minus T delta S. Yes, either your temperature is too high or your change in entropy is too high, or both. That can negate the total value to a negative number. Try to understand. Okay, try to understand this as delta H is 100. Okay, plus 100. But the T delta S is plus 400. So when you subtract T delta S from delta H, the total result will be minus 300, which is a negative number, which is the value of delta G. Therefore, the process becomes spontaneous. So it is possible for a positive positive enthalpy reaction to be spontaneous in two conditions. First condition is you increase the temperature to an appropriate value, or the entropy change is really high and positive, right? But there is absolutely no reaction in the world for which delta H is positive and delta S is negative and it is still spontaneous. Why? Because delta H is positive and T delta S, because delta S is negative, T delta S is also positive. So delta G can never be negative in this case. And if delta G is not negative, the process is not spontaneous. Right? Now let us move to Gibbs energy change and equilibrium. We'll see the change in Gibbs energy and relate it with equilibrium, and then we'll look at all the things together. We have seen how a knowledge of the sign or magnitude of free energy change of a chemical reaction allows prediction of spontaneity and prediction of useful work that can be extracted. Okay, now what is the difference between delta G and equilibrium? At equilibrium, what should be the change in free energy? Suppose A, B gives C, T, this reaction is in equilibrium. So if we try to deduce some reasoning, we will find that delta G should be 0. Because if free energy change is happening, then the reaction will tend to move either forwards or backwards, okay, towards a less energy state. But since the reaction is neither moving forwards, neither moving backwards, it is in an equilibrium, we can easily say that free energy change is 0 because the system has reached minimum amount of free energy. This is the least amount of free energy that both the reactions and reactants and products can possess, and they are interchanging into each other. Okay. If it is not 0, the system would spontaneously change to a configuration of lower free energy, right? So the criteria for equilibrium is this. Next, Gibbs energy for a reaction in which all reactants and products are in standard state is related to the equilibrium constant of the reaction as follows. So delta G is equal to delta G naught plus RT ln K. This is another equation for Gibbs energy. There is something called standard Gibbs energy and there is something called Gibbs energy. The standard Gibbs energy is only for when all the products and reactants are in standard state. And I think they are not given it previously. I'll just write it here. Delta G is equal to delta G naught delta delta G naught plus RT ln K equilibrium. Okay, this is the equation. Now, on rearranging the equation, we find one more useful equation, which is delta G naught is equal to minus 2.303 RT log K. This is delta G naught, okay, not delta G. And from delta G naught, we can also find out this equation, which relates enthalpy, standard enthalpy, standard entropy change with the equilibrium constant. And this is always valid because at equilibrium, delta G is 0. Now, for strong endothermic reactions, the value of delta H naught may be large and positive. In such case, value of K will be much smaller than 1 and reaction is unlikely to form much product. So if it is a highly endothermic reaction, delta H may be large and positive, K will be smaller than 1 and product will be much less than the reactant. But for exothermic reaction, this is the first. For exothermic reaction, delta H naught is large and negative, delta G naught is likely to be large and negative too. So K will be much larger than 1 and product will be much more than an endothermic reaction. Right? Okay. Now let us examine this table before we move to the, okay, there is one more deduction we can do from the equation. It is possible to obtain an estimate of delta G naught from the measurement of delta H and delta S naughts. Then calculate K at any temperature for economic yields of product. So this is a use. The second one is also use that the K or the equilibrium constant is measured directly in the library. Then the value of delta G naught can be calculated at a temperature. Now let us examine this table. First point is if enthalpy change is negative, entropy change is positive. Definitely the delta G will be negative and the reaction is spontaneous at all temperatures. Second is if enthalpy is negative, entropy is negative, then only at low temperature the reaction will be spontaneous. Again, at high temperature, the reaction will be non-spontaneous. So these two are similar. Thirdly, if the entropy is positive and enthalpy is also positive, then at low temperature the reaction will be non-spontaneous. And only at high temperature the reaction will be spontaneous. Okay, we can all predict this from the equation. Just I'm revising the table for you. Now, if delta H is positive, delta S is negative, which I had told, it will be non-spontaneous at all temperatures. So the fourth point is, there is no way to turn it into spontaneous because delta G will always come to be positive. All right, so we have done with the chapter. We can move to the questions now. Okay, before that, let us once see the summary and then we can proceed with the questions. So thermodynamics, we had seen a zeroth law because right now we'll do all the questions together, just like we were doing yesterday. We will do some PYQs in which we will use multiple concepts. So let us revise the whole chapter first. Zeroth law says, if there is a body A which is in equilibrium with a body B and a body B which is in equilibrium with a body C, then A will be in equilibrium with C. Yes. This is what the zeroth law says. After that, we had discussed about state variables, path functions, your So we had discussed state functions, path functions, your extensive values, extensive properties, your intensive properties, how to find out if it is extensive or intensive. We had determined the work, the heat, kinds of processes like adiabatic, isothermal, isobaric, isovolumetric, right? Now, from these, we reach the first law of thermodynamics, which is delta U is equal to Q plus W. This is a basic law, and we need to remember this at all times. Internal energy change is a state function which depends on two path functions. Okay. So heat and work are path functions. Now, after determining the internal energy, we had seen that most of the reactions are carried out not at constant volume but at constant pressures. So we defined one more term known as enthalpy. One more state function, which is enthalpy. So what does enthalpy tell us about the state? It tells us the total energy in a constant pressure change. So enthalpy is basically the heat transferred at constant pressure, whereas your change in internal energy was heat transferred at constant volume. Okay, right. We had defined a relationship between enthalpy and internal energy also using some gas functions and temperature. After that, we had calculated the heat capacity. We had defined the heat capacity. Lot of questions are asked on the heat capacity, so it is quite an important term. We had defined heat capacity at constant pressure and constant volume also. We know that there is a function called gamma, which is Cp by Cv. We had seen Cp minus Cv is equal to R. All these we had seen. We had also seen that heat capacity has three forms. One is normal heat capacity, which is capital C. Then we have small c, or specific heat capacity, which is total heat capacity divided by total mass. Then we have Cm, which is molar heat capacity, which is heat capacity divided by the total moles. Out of these, I think specific heat capacity is the most useful, and you need to define Cp and Cv for this function. Then we had seen various types of enthalpies. Okay, various kinds of enthalpies, like enthalpy of atomization, enthalpy of lattice, enthalpy of solution, enthalpy of reaction. Out of these, I think the most important is enthalpy of formation. And enthalpy of formation, because enthalpy of formation requires the reactants to be at standard states or states of references, which, if you remember, I'll give you some examples. For carbon, graphite is the reference state. For oxygen, it is the dioxygen gas. For nitrogen, it is again the dinitrogen gas. For sulfur, it is the rhombic sulfur, and so on. Okay, which determines the heat of formation. Then we had seen the enthalpy change in a reaction, which is basically the enthalpy of all the products and subtracted by enthalpy of all the reactants. What was Hess law? If we try to remember what Hess law is, it says whatever path you may follow for obtaining the same product from the same reactant, the enthalpy change will be equal. It will be same. The net enthalpy change will be same, which means this is A and this is B. If you go directly from A to B, you get a delta H. But if you take another path, like from you go to C, you turn it to D, you turn it to E, then you turn it to B. And all these enthalpies, when you add all these four enthalpies, they will be equal to the total enthalpy change, which was when you directly converted A to B. That is what Hess law is. Now, there is an important relationship between the delta H of reaction and the bond dissociation enthalpy. The delta H of reaction is bond dissociation enthalpy of all the reactant, minus bond dissociation enthalpy of all the product, and it is the sum of them. Yeah. So the bond enthalpies of reactants minus bond enthalpies of product. This implies that if the reactants are having higher bond enthalpies than the products, the reactants are more stable because their bond energies are higher, which means in transforming the reactants into products, you have to supply some energy. So delta H will be positive, which is evident from the relation and this equation. Okay, everything has a explanation in thermodynamics or in chemistry. Next, we covered entropy. Before entropy, we had seen spontaneity. For spontaneity, we saw enthalpy is a really important variable or function, but we saw that enthalpy alone cannot drive a reaction because it had some contradictions. So we defined one more term for it, which was the entropy. And the entropy is the degree of randomness of the system. After defining entropy, we tried to figure out a relationship between the two, which might give a direct relationship or which might directly indicate the spontaneity. And we found out what? We found out another state function, which is the Gibbs energy. In our quest to determine the relationship between entropy and enthalpy in determining the spontaneity, we found out Gibbs energy. Yeah, this formula is important for entropy, so you remember. Now, Gibbs energy was the free energy available to do work, and it also determined the spontaneity. So for a spontaneous change, delta G is equal to negative. For a non-spontaneous, it is positive, and at equilibrium, we saw it is 0. Then at equilibrium, we defined one more equation with the standard Gibbs energy and with between the standard Gibbs energy and standard enthalpy and entropy change. Right, this is what all we have covered till now. Let's move on to some PYQs of last year's JEE-Main. Okay, we had solved almost six questions. Let us move to the 7th one. The enthalpy change for the conversion of half chlorine to chloride ion aqueous is. So they have given us this, and the hydration enthalpy and bond dissociation enthalpy and enthalpy of this is the electron gain enthalpy of chlorine atom. Okay, so we have to use Hess law here. Let us first form the flow chart to understand how Hess law is practically used. So we have to find this delta H, right? And this is the reactant and the product. We have to use these information to change the reactant into the product using Hess law. Let us see. First of all, we have half chlorine. We will break it into chlorine gas. From the chlorine molecule, we will break it into chlorine gas. So what will we use here? We will use dissociation energy for chlorine. But you can see that it is only half of chlorine. So half of this energy will be used. Done. We have obtained the chlorine atom here. Okay. Now we will turn the chlorine atom into chloride atom. Okay. We will give an electron to the chlorine atom to turn it into chloride atom. Here also there will be an energy change, and this energy change will be this enthalpy change will be the change in electron gain enthalpy. Okay, now we will hydrate this chloride atom. We will put this into a solution, and in doing so we will be obtaining our product, which is chloride in aqueous solution. But here the enthalpy change will be hydration of chloride gas. Okay, so in short, what we have to do, we have to add half of dissociation energy, complete of electron gain enthalpy, complete of hydration enthalpy. So let's add 1 by 2 into 240 plus minus 350 plus minus 380, which gives us 7 minus 730 plus 120, which is minus 610 kilojoule per mole of energy. This is the total enthalpy change for conversion of chlorine to aqueous chloride. Okay, so you saw how Hess laws is being used. We saw that we have used about 3 different enthalpies, but we were able to find out our desired enthalpy by relating all of them through a series of your reactions, and these reactions were able to help us in finding out the total enthalpy change in the reaction which we deserve. So we have to create a loop, we have to create an alternate path, we have to create a chain of different reactions linking the reactant with the product. Okay, then only we can apply and we can use the individual enthalpies and find out the enthalpy which we need to find. Right? This is how Hess law works. Let's move on. Enthalpies of formation of CCl4, H2O, CO2, HCl are this. The magnitude of enthalpy of the reaction given below is, so they have given us the enthalpies of formation and they are asking for enthalpy of the reaction. Simply we will subtract the enthalpies of formation of reactants from products. Okay, simply we will subtract the delta HF of reactants from the delta HF of products. Let's calculate. For the products, we have to see the coefficients 4 and 2. We should not skip these. So 4 into minus 92. For CO2, it is minus 394. For H2, it is 2 into minus 242. For CCl4, it is minus 105. So the equation comes out to be, okay, 4 into minus 92 is 360. 8. 2 into 242 is minus 484. So for products, minus 394 minus 368 minus 105 minus 484. Okay, which comes out to be minus 762 minus of 589. So basically it is minus 762 plus 589. Okay, it is minus 1. 100, sorry, minus 73 kilojoules per mole. So this is the enthalpy change in the reaction. Moving on, 0.3 gram of ethane undergoes combustion at this temperature, which is convert it into 300 Kelvin, right? You can always convert degrees Celsius into Kelvin. In a bomb calorimeter, what does bomb calorimeter mean? That volume is constant. Delta U is, oh, so sorry. Volume is constant and work is 0. Delta U is only equal to Q. Now, the temperature of calorimeter is found to raise by 0.5 degrees Celsius. The heat evolved during combustion. So they have given us the temperature raise in the calorimeter. They want to calculate the heat evolved in the combustion of ethane, but they have added a catch. It should be at constant pressure. Here, using a bomb calorimeter data, we can find QV, which is basically the change in internal energy. But they have asked us for QP. So we have to find delta H from delta U, which we can easily do by the equation that we know. So let us try to find QV first. Okay, they have given us the heat capacity of water or the calorimeter. Heat capacity of the calorimeter is 20 kilojoule per Kelvin, and the temperature of calorimeter was found to increase by 0.5 degrees Celsius or 0.5 Kelvin. So the heat transferred at constant volume in the calorimeter, heat evolved was 20 into 0.5, which is 10 kilojoules, right? This is equal to the delta U. Okay. Now they are like assuming it as an ideal gas behavior, so we can directly use this relation delta H is equal to delta U minus delta Ng RT plus. I'm so sorry. We should not assume we should just write the formula first and then assume the signs. Delta H is QP, which is our answer here, and delta U we have already found out, which is plus of 10 kilojoules, and delta N. Okay, this is for finding out the delta N of gases. We have to write the equations. Let us write the equation. Combustion of ethane. C2H6 is ethane. When it undergoes combustion, it will give 2CO2 and 3H2O, right? So 2 plus 1.5, so 3.5 O2. Okay, 3.5 O2 is what 1 mole of ethane needs to be converted into product. How? Because 2 oxygen and here 1.5 oxygen. So total, okay, ethane will be a gas, oxygen will be a gas, carbon dioxide will be a gas, water, it is 27 degrees Celsius. So water will be liquid here. Delta N of gases is how much? Minus of, because okay, we'll not assume signs, we'll just write the values. It is product, which is 2 moles of carbon dioxide minus 3.5 minus 1. This gives us minus 2.5, right? We will put it here, minus 2.5. R they have given into 8.314, and T they have given 300 Kelvin. This will give us, this is in joules, so we have to divide all of this by 1000. So QP is equal to 10 minus 5/2 into 25/3 into 300 divided by 1000. So I have written 8.314 as 25/3. This is absolutely valid, okay? Yeah. So answer is 3.75 kilojoule per mole. If we round it off to the nearest integer, it comes as 4. Right. So this was all the questions, and we are almost done with the chapter. We have revised the chapter, and yeah. Thank you, everyone. We will do the thermochemistry portion in the next session.